So go ahead. The floor is yours, Alex.
Thank you, Avi. Just please remind me, how much time do I have?
I think at 1 hour, but
okay.
I will...
Yes, it is 1 hour.
Okay, perfect. So first of all, thanks for the introduction. Thanks for the invitation. It's great to be here, even though virtually. So I would like to make a disclaimer. So I indeed work on many topics, but I have never touched anything related to hardware security or hardware verification, and I don't consider myself an expert on graphs. But basically what I would like to do, I would like to show some of the work I have been doing, let's say in the past 10 years, in the field of geometric shape analysis of three-dimensional shapes. And I will try to convince you that there are interesting tools that are potentially useful. I'm not claiming they're useful. I can probably claim that some of them are useful because I tried them. Useful for the graph processing community, and for specific applications related to hardware. So Amit Boyarsky, who will speak after me, will make some more concrete references to graphs. So just try to apply your imagination. I'm going to show you tangible three-dimensional shapes like you often encounter in geometric modeling and computer graphics, but I will think of them most of the time as continuous smooth manifolds, discretized as a mesh. But just apply your imagination and think of them as a particular instance of discrete objects that can be represented as graphs. And basically, some of the tools that I will try to advocate could be useful tools and representations, and ways of thinking could be useful for graphs. I'm not claiming that all of them are necessarily easy to adapt or to adopt to the needs that arise in graph analysis, but I guess many could be adapted. So without further ado, I would like to show you some interesting things. And I don't know, can you ask questions in real time, or do we need to wait for the end of the presentation? How does it work?
This is up to you. If you
I will be happy to be interrupted by questions. I will.
Okay, so as soon as somebody will pose a question, I will interrupt you, or you can look on the Q&A slide that you have, and so you will see the Q&As as well. But if you don't like to be bothered by looking on too many screens, I will just ask the questions. It's up to you.
Okay, so let me try. I will try to connect with my second device and see if I can view the questions in real time. So I will just try to do it now. But I would like to first of all thanks my I would say long-term collaborators. These nice folks with whom I've been working on these and other topics for many years. So let me start with the setting of the problem that I would like to address. So the problem is finding correspondence between two surfaces, two three-dimensional objects. So imagine the boundary of a tangible physical object. This is a two-dimensional surface, right? It's a two-dimensional manifold embedded in the three-dimensional space. We can touch it with our fingers, and we would like to find a map that brings points on manifold X to points on manifold Y. So we would like to find a pointwise map. Okay, and of course in graphs you can think about similar correspondence problems that bring nodes into correspondence. Typically, the way you would like to find this correspondence is by minimizing by the discrepancy of some some local properties or maybe some global properties. So basically, I will touch upon what exactly you would like to put as a criterion for this correspondence problem. In graph, we typically look for minimizing the disagreement between adjacency matrices, and this is when it is exact, it is called graph isomorphism, right? And when it is inexact, we can talk about different ways of speaking of partial graph isomorphism or approximate graph isomorphism. But basically, before talking about which criterion to minimize, let's talk about the representation of this thing. So we have this pointwise map between two continuous surfaces or their discrete representations. This map by itself is not an easy object to deal with. Surfaces don't have global parametrization spaces, at least not something that necessarily comes naturally or easily. And even representing this object, this pointwise correspondence, is not a trivial problem at all. Okay. In a graph, you can think of this object as a permutation matrix, right, between the vertices of two graphs. But what happens if the graphs don't have the same number of vertices? If the graph represents some continuous object, they might be sampled differently and different number of points with different density. And what if the graph has billion vertices? 1 billion vertex permutation is not an easy object to work with, right? So I think a brilliant idea was proposed by Max Ovsyannikov and his collaborators about 10 years ago in his PhD that he did at Stanford in Leo Giba's group. So basically, the idea was, which is actually it's a very natural idea if you think about it. It is often this kind of recipe is often used in mathematics and in various applications. If you have an object that is complicated to work with, like a complicated map between two relatively simple spaces, lift it to a space of more complicated objects, but then maybe you will enjoy some simple structure. So instead of thinking of a map that takes points to points, think of a map that maps functions to functions. You can define a function on one manifold, let's say square integrable function on manifold X, square integrable functions on manifold Y. On a graph, functions would be just vertex fields, and think of a map that maps one function on one manifold to another function, corresponding function on another manifold. Like, for example, if we paint this cat's paw with some scalar field, we would like this object to advect, to carry this carry this correspondence to the other manifold in a way that it looks meaningful. So again, the space of objects now complicated a lot, right? Instead of having maps between points on manifolds, we have maps between two function spaces. But what we got in exchange is that this operator T that now represents the correspondence is a linear map. And it is arguably easy to work with linear operators. Okay? So basically, we complicated the space in which we represent correspondences. In exchange, we received linear maps. Okay, and I think this is a brilliant idea, and it had so many ramifications and follow-up works in the decade that followed. So essentially, just to summarize this idea, you have a function f on one object, you apply to it an operator t, and you get the corresponding function g on the other object, right? And if you know how to describe this operator t, you got the correspondence, right? We'll get to the question, how do we actually recover the pointwise map from this representation? But basically, working with the standard basis might be unnecessarily complicated. Like, again, think of a graph with a billion vertices. Basically, you need, this operator is a billion by billion matrix, right? It's not necessarily an easy object to deal with. So what we could do, we could equip each of the objects that we would like to bring into correspondence with an orthonormal basis, with a pair of orthonormal bases. We have an orthonormal basis for the cat, and we have an orthonormal basis for the dog. So essentially, one of the most one of the easiest representations for such for one of the most natural choices for an orthonormal basis is the harmonic basis. These are the eigenfunctions of the Laplacian operator that have a clear physical or signal processing interpretation. It's the analog of the Fourier basis. The analog of the Fourier basis on manifolds. And of course, this can be defined on graphs as well. I mean, it will show some more details about how to construct Laplacians on graphs. So I will denote the basis functions by phi and psi. Okay. By the way, any questions? Any questions until now? Okay, so I will. So anyway, if you have any questions, please.
Nothing at least show up on the Q&A.
Okay. Okay. So we take these two bases and we can decompose any function, any scalar valued function on the cat into a Fourier series with the coefficients a on the cat's basis, and we can take the corresponding function g on the other object, on the dog, and also decompose it into the Fourier series with respect to the other basis with the coefficients b. So now we can represent this operator t with respect to this new pair of bases, so one for the column space, another one for the row space, which I will denote by this operator c. So it's the same linear operator, just represented with respect to different bases. The advantage of the Fourier basis is that we can truncate it, and then let's say we truncate it after k harmonics. So we have a matrix k by k, c, that approximates this correspondence. And this, using the signal processing jargon, would be a band-limited approximation of our correspondence. So it will blur some high-frequency details. And of course, we can choose different bases that have different properties, but working with the harmonic basis is a very natural choice. You essentially create a scale space of representations. And there are some recent works that explicitly use this scale space to gradually improve the resolution of the correspondence. But I won't talk about it in detail. I will be happy to give you references on that. So essentially, how do we solve for correspondence between these two objects? It becomes an algebraic problem rather than a geometric problem. So if we are given functions g and f, let's say we have a function f and we know that there is another function that is also given g that is in correspondence, that is a corresponding function to f, like these two red functions that we have on the cat and on the dog, they are going to be related by this linear map t. Or in the Fourier domain, we have this linear map c that relates between the corresponding Fourier coefficients. So now, if we are given some amount of, let's say, q of probe functions, fi and the corresponding function gi, we can just stack them into a matrix. Let's call them A and B. I already write them as the Fourier coefficients, A and B. And we just solve a least squares problem for C. And C represents the correspondence. So you see, we reduce this potentially complicated problem of finding correspondence between shapes into a simple least squares problem, into a simple algebraic problem, solving for C. Okay. So still, I'm not telling you how to go back from this representation to the pointwise map. In many applications, this representation is already a good representation to work with. For example, if we want to transfer some property from one graph to another, we can just multiply that property by the appropriate linear operator. But sometimes we'll need the pointwise map, and I will tell you at the end how to get it. Okay. So basically what I'm going to do, I'm going to take my object, take my manifold, and I'm going to assign to each point on the surface a k-dimensional vector. Let's call it a descriptor. It's a pointwise descriptor. This pointwise descriptor will tell me some information about probably some local neighborhood about that point. This can be anything. This is a descriptor. If I manage to build a process that creates such vector value descriptors, dense vector value descriptors for the manifold in such a way that it will be repeatable across, let's say, different shapes and invariant to some set of deformations, then I can use these descriptors as probe functions to solve for the correspondence problem. So one of the typical things that could be used here that is invariant to a wide class of transformations that are called isometric transformations, something that doesn't change the metric of the manifold. Like, for example, non-rigid articulations that don't stretch or compress the manifold would be isometric. And as a result, the Laplacian will not change. So anything that can be expressed in terms of the Laplacian, something that is called intrinsic properties of the manifold, will stay invariant. And some of these intrinsic properties can be actually very stable and numerically computable in a very stable way. So Amit will tell more about this. One of the particular types of descriptors that can be used and actually widely and successfully used in shape analysis are the properties of the heat kernel. That is simply the solution, the fundamental solution, the green function of the heat equation on the manifold or on a graph. And basically this heat, the property how much heat stays at a point after some time t is something that can be used as an intrinsic descriptor. So for the sake of my presentation, I will just assume that there is some descriptor that we can compute at every point on the mesh or on this manifold or on the graph, and then we are going to solve for this least squares problem. So one of the questions that arise immediately, so if you have some descriptor that you constructed in some principled way, for example, using heat properties, will it be useful for a specific end task? And basically, this problem has been addressed in computer vision for many years, and of course, in the era of machine learning, descriptors are actually not constructed by hand, but are learned from some raw data, some raw properties that can be constructed, and the learning mechanism will actually determine what basically what transformation of the descriptor is important for some task, and will typically find both robustness and invariance if the raw data are rich and informative enough. So the standard way of learning a descriptor, and I will just try to translate it into our setting. So we used what is called a short descriptor, which is not an intrinsic descriptor, it's just a histogram of the normal vector on the manifold. This is something that doesn't exist naturally on a graph, but again, on a graph, some other intrinsic descriptor would be more appropriate. So we take the two shapes, we compute some raw descriptor on each point of the shape, then we process them with a neural network. So we take shape X and shape Y, we process them with the same neural network, and then we compare the two descriptors F and G that are obtained. Basically, the F and G are just n by k matrices, where n is the number of rows, so a number of nodes, and k is the number of dimensions in the descriptor. And what we are going to do, we are going to create a training set of points that we know that are either in correspondence or not in correspondence. It's typically very easy to create points that are not in correspondence. If you just sample 2 points at random from X and Y, with overwhelming probability, they are not going to be corresponding. And for corresponding points, we actually need some ground truth data, which is expensive, and this is something that I would like to address next. How do we avoid this altogether? So if we have these kind of pairs or triplets of points, let's say X and X plus, which are known to be in correspondence on X, and X and X minus that are known not to be in correspondence, basically we would like to find descriptors such that similar points have similar descriptors, and dissimilar points, non-corresponding points, have dissimilar descriptors. And this is an obvious thing to do, right? The problem is that when we learn such a descriptor and we use it within these functional maps, within this linear operator representation of correspondences, we find that learning the descriptor actually doesn't improve the correspondence quality. So what you see in these two plots, on the left, it's the the typical CMC curve. It shows how many, it shows the hit rate of the original raw descriptor versus the learned descriptor with the Siamese neural network architecture that is typically used in the descriptor learning literature. So essentially, it shows how many correctly matched descriptors are found in the first K matches. And of course, learning improves that because this is exactly what we're learning for. But when we actually examine the quality of the correspondence, instead of taking the first best matches, we look for some radius around the point. And we would like to say that I want my correspondence to be exact within a certain tolerance radius. I don't want my corresponding point to be thrown, let's say, more than epsilon units of distance away from the ground truth correspondence. Then you see that the learned descriptor practically improves nothing because it is completely agnostic to the process that is going to be applied to the descriptor. So basically, the trivial thing that we did in this work some time ago. Oh, okay. So I have a question: what x minus and x plus represent? So let me go backward to this slide. So a triplet x, x plus, and x minus is a triplet of points. X is some reference point. X plus is a knowingly corresponding point, and y plus is a knowingly non-corresponding points. And I apologize. It should be, of course, it should be G on the other side. So it's F and G. We would like the descriptor in the corresponding point on the other shape to be matching the descriptor on X. So we want the descriptors on X and on Y to match at corresponding points. And we would like the descriptors on X and Y to be distant from each other. That's why we have this hinge loss here, distant at least by mu, units of distance in the descriptor space, if X and the corresponding point on Y are not corresponding. So basically, we have this set of triplets, X and the corresponding and the non-corresponding points on the other surface Y. Okay, I hope this answered the question. So essentially, what we are going to do, we are going to build this pipeline until the end. So we will incorporate into the learning loss not only the transformation of the descriptors themselves by this nonlinear neural network, but also the way the descriptors are going to be used. Okay, so basically what we are going to do, we are going to take these raw descriptors, project them onto the corresponding Fourier basis, phi and psi, okay, and get their Fourier coefficients A and B. Then we are going to solve for this functional map, which is a least squares problem. So we solve for C that matches between A and B, and the output is this C. Okay, so basically this is what the functional map layer, if you think of it as a layer in a neural network, this is what it does. It solves the least squares problem. What we are going to do now, so C is a spectral representation of the correspondence. We can actually project it back onto the standard basis, right? It will be some kind of a blurred version of a permutation. It is a blurred correspondence. We can think of it as a soft correspondence. We'll just take, because we truncate the Fourier basis, we might have negative values. So we'll take the absolute value and we'll normalize it in such a way that it represents probability. Okay, so we'll call this a soft correspondence layer. So this probability essentially, you can think of the output of this soft correspondence problem as the probability of mapping a point into some distribution on the other shape. So that distribution is the probability of a point on Y, on this right-hand shape, to be in correspondence with the green point. And this is the probability distribution of the red point, and this is the probability distribution of the blue point. So it's kind of a fuzzy or soft correspondence that we are obtaining in this way. And now with respect to this probability distribution, we can define a moment. We can define, for example, we can define this moment with respect to this probability distribution again, let's say of the squared geodesic distance of the point Y from the ground truth correspondence pi star x. Pi star x is the ground truth map on Y of the point X, right? So we know this correspondence. This is our ground truth. And we would like, of course, this distance to be as small as possible. Now, when we write this sum weighted by the probability P, it is essentially an approximation of the expectation operation with respect to this probability P. Okay, when we do this trick, basically we do end-to-end learning. The correspondence quality as the result of this learning improves quite dramatically. So we call this idea FMNet. So it's just a neural network that is the revisitation of the Siamese neural network, basically Siamese metric learning or descriptor learning, but with an end task incorporated into the learning scheme. And the end task again includes this functional map, which is a least squares problem. It has stable gradients that can be computed and backpropped, and it has the soft correspondence layer that is given this probabilistic interpretation. Okay. So again, in our training regime that I described, we had this. It was a supervised regime, right? Basically, it was supervised by the ground truth correspondence. We need to have the ground truth correspondence in order to be able to solve it, and that might be costly. It might be costly to obtain shapes, many shapes for the training set that have ground truth correspondence. And the question is, can we do without ground truth at all? Okay. So the question was, why to define the second moment instead of the value of n? What is n? So I'm not sure I understood the question. Oh, okay. So I'm not sure I understood completely, but basically d squared. So d squared. Let me just take you back to this slide. So suppose, can you see my mouse? So this is point X, and suppose that the ground truth corresponding point pi star X is somewhere here. So instead of getting a sharp correspondence, I get some blurry version. I would like this distribution to be concentrated around the ground truth value. How do I measure the concentration of this distribution? I measure it using the second order moment. The second order moment has two terms that I need to minimize to get concentration. One is the bias term. It's how far I am, how far is my center of the distribution is from the ground truth point. I can improve it by making the correspondence more correct. And it also has some spread. It also has some variance. The variance stems from the fact that we truncated the Fourier basis. That cannot be reduced. That depends on the number of dimensions that we have in the harmonic basis. But I can still remove the bias term. And this is what we are trying to do. When I write this loss function, I'm essentially trying to reduce this bias term as much as I can. Okay? So it is meaningful actually, but because of this blurring, it is also stable. And of course, it involves much less degrees of freedom than solving it in the original domain. Okay? So I hope this answered the question. So now the question is, how can we use no ground truth at all in this problem? Okay? So one of the settings that is interesting, suppose I give you two shapes and no training set. So I show you two shapes from two classes of objects that you have never seen in your life. Something completely new, something novel. Can you use those shapes as the training set? Can you train on the same data you are going to infer on? So this is kind of a self-supervised learning setting. So again, this was our supervised loss, but let's think about an unsupervised loss. So we used for the supervised training loss, we use this notion of a geodesic distance, some intrinsic distance. It doesn't need to be a geodesic distance, by the way, but some intrinsic distance, some meaningful distance on the shape. On the graph, there are many ways to define meaningful distances. It could be a diffusion distance, for example. It could be just a regular graph, shortest path length in the graph. If the graph has small dimension, it would actually be a very meaningful distance. So what we could do instead, what we tried to do before was to match pointwise correspondences, but we can try actually matching here pairwise quantities. So a distance between a point x and x prime on the shape x is a pairwise descriptor. It tells us something about the structure of that domain. So if we map x and x prime to 2 points y and y prime, there will be some distance dy between y and y prime that is corresponding to dx. And we would like, ideally, these distances to match the discrepancy between 2 be 0. So of course, we don't really map X into a Y. We map X into a distribution around Y. And we don't map X prime into Y prime. We map, again, X prime into a distribution. So if you now look at this sum, what is written here is the expected value of dy, right? With respect to that probability distribution. It's actually, what is written here is a product distribution of two independent marginals. So what we can see is the measure, the L2 measure of discrepancy between dx, the metrics of pairwise geodesic distances on X, and the expectation of the geodesic distance on Y, composed with this joint measure, joint probability distribution, P cross P. Okay, and we can minimize this. And for that, you don't need any ground truth correspondence. Your proxy to a good correspondence would be minimal discrepancy of these pairwise distances. So this leads to an unsupervised loss and an unsupervised setting. Okay, and of course we can train either the supervised or the unsupervised loss on some representative class of shapes. Okay, or we can work in the self-supervised regime with at least with the unsupervised loss. We can train on the same shapes that we are going to match. So imagine that you have two shapes. Let me now speak in terms of graphs. Imagine you have two graphs on which you would like to solve the graph isomorphism problem. Now, the graph isomorphism problem can be written exactly in this way, as trying to find a permutation or a map that minimizes the disagreement of the adjacency matrices or some other notions of adjacency between the two graphs. This, however, is a quadratic assignment problem. It is a very hard problem to solve. So instead, what we are going to look, it is hard to solve because we need to deal with pairwise quantities, like distances or adjacencies. If instead we train descriptors, which are pointwise properties, and pointwise properties can be brought into correspondence by linear assignment problems, which are much, much easier to solve. We train pointwise quantities, we solve simple correspondence problems like this least squares problem that I showed, with the attempt to solve a much harder problem of bringing pairwise quantities into agreement. So again, we learn the descriptor on the pair of the same two shapes that we need to bring into correspondence, but solving it directly is a very hard problem, doesn't scale well. So we learn the descriptor that will minimize the loss. That is exactly what we are trying to minimize and have a hard time minimizing. So we learn this descriptor and then solve a proxy problem, basically this functional map problem, that will be minimizing this pairwise criterion. And instead, so of course we can take any combinations of supervised and unsupervised losses. We can have some supervision on some shapes or on some points that are given in supervision and lack of supervision on the rest. So just to visualize that this unsupervised loss is a meaningful one, see that when we minimize the unsupervised loss, which is this green curve, the supervised loss also minimizes. So it is a meaningful process. Okay, so I have a question to repeat the unsupervised strategy again. So let me now try to tell it in different words in terms of graph isomorphism. So the problem of graph isomorphism is to bring, maybe let me see if I can write on my iPad. Hope you can see it writing. Just a second. So let me try to share my screen. Can you see my screen? I think I should be able to see my screen now.
Yes, we can see your screen.
Okay, perfect. So in a graph isomorphism, you are given two graphs. Let's continue calling them X and Y. And I would like to bring into correspondence, let's say, an adjacency matrix on X and the adjacency matrix on Y. And this is my permutation that brings them into correspondence, right? If I can solve this perfectly, pi is a permutation, n by n permutation. Suppose I have the same number of nodes into graphs. So instead of A, I can write any pairwise quantity like the distances or some other pairwise properties on the graph. If I can solve this problem exactly, this would give me the graph isomorphism, right? Now, matching these two matrices is a quadratic assignment problem, right? It's a very hard problem. It is not even known whether it is in P or NP. It probably belongs to some separator. It's not probably, it's a known result. It belongs to the so-called GI class that is not known to belong either to P or to NP. Okay, but practically it is a very hard problem. So what I'm doing instead, I'm learning a pointwise descriptor. So if I have pointwise descriptors, so again, let's write this as F and G. So matching pointwise descriptors looks like this. So this is a quadratic assignment problem, and this is a linear assignment problem. Linear assignment problems are easier to solve. Can you see it? So if I learn descriptors F and G such that the minimizer of this linear assignment problem gives me the minimizer of the quadratic assignment problem, I essentially circumvented the solution of the complicated quadratic assignment problem, the graph isomorphism problem, by solving a much easier problem of descriptor matching, of pointwise descriptor matching. And this is exactly what we are trying to do here, okay? So I hope this answers the question. So again, we are looking for this. So I'm just instead of having pi, the permutation in its sharp form, I'm using some kind of a blurred soft version of the permutation in which basically a point, let me just draw a point x on domain x maps into some blurred distribution on domain y, okay? And basically the value of this distribution is pxy. You can think of it as a density function, right? So just going back to what I showed before. So if I train to minimize this unsupervised loss, the supervised loss that reflects our ground truth knowledge of correspondence is also minimized, which at least in these articulated shape examples amounts to the fact that this kind of pairwise descriptor, these geodesic distances, are a good proxy to the actual semantic correspondence that lies underneath this problem. Okay. So this is just what happens when we solve the correspondence problem. So I still didn't describe what PMF means, but basically what is important is to see the discrepancy between the red curve and the black curve. The red curves and the black curves practically match. Minimizing the unsupervised loss is slightly inferior, but very slightly so. And unsupervised loss, of course, requires no ground truth correspondence. So we just rely on the disagreement between the geodesic distances, which can be computed automatically, rather than asking somebody to mark corresponding points on our shapes. So this is just a visualization. It is typical in this community of computer graphics to show the quality of correspondence by mapping high frequency texture from one shape to another. Our eye immediately captures bad correspondences because the texture becomes crappy. So you can see this is the reference and these are corresponding shapes. The texture maps actually quite nicely with high quality details. These are just the plots that I showed before. What you see on the horizontal axis is a tolerance radius, and on the vertical axis, how many corresponding points fall within that tolerance radius. So it's kind of a cumulative distribution plot for the correspondence error. Okay, and you can see that the unsupervised region with some post-processing that I will describe in the sequel actually gets almost perfectly the correspondences with very low tolerance. Okay. So another interesting property, I can also solve for partial correspondence. I don't have time to talk about partial correspondence. So we have actually a sequence of works that we did in the past few years dealing with the partial correspondence problem. Yes.
Yeah, we can't see the slides. We still see the whiteboard or the blackboard.
Sorry about that. Apologize.
Yeah, you are still on the.
I think I had two shares actually. I think I had two shares, but let me.
No, right now you share only the blackboard that you have is the 1 point,
Okay.
which is back. Okay.
So let me share my screen again. Can you see my screen?
Yeah.
Okay.
Right now we see the partial correspondence. Yeah.
Okay. So the point about partial correspondence, again, I don't have time to talk about. Basically, partial correspondence actually requires separate ways to be addressed. I think we have a few very elegant formulations for how partial correspondence can be written entirely in the spectrum domain, basically just extending this notion of functional maps to the cases where the function is the domain and the codomain of the function are restricted to a proper subset of the two shapes, and these two subsets are unknown. But basically, again, I will be happy to give references. I don't have time to talk about it. But what I would like to show here is that even though the correspondence hasn't been trained, these descriptors haven't been trained on partial correspondence, actually doing this unsupervised training with distances which, of course, are sensitive to partiality, actually works on par with a sophisticated functional map framework that has been extended to explicitly deal with the partial setting. So this learning, at least this is a byproduct that we didn't aim at, but we got it again as a byproduct, is that this learning seems to gracefully deal with the partial setting, even though it hasn't been trained for it. Okay? And of course, we need to do the training that takes into account the partial correspondence. All this has to be done. We didn't do it yet. Some visual results, I think I will skip them. Maybe just a few words about the unsupervised loss itself. So the way it is written here, you actually need to materialize the distance of the matrix of pairwise distances in the original basis. So this norm is written in the original basis, and this P actually is written in the original basis as well. So if you have again a graph with a billion points, this is a 1 billion by 1 billion difference matrix, of which you need to take the L2 norm, which is kind of difficult to compute, right? So what we can do instead, we can project this norm onto the truncated Fourier basis, onto the truncated harmonics. Basically, these are phi and psi, right? So instead of getting 1 billion by 1 billion, of course, with some approximation, band limited approximation, we get some k by k matrix. K can be a few hundreds or a few thousands. So then P, of course, can be written in terms of our functional map C. So you see this unsupervised loss is now fully expressed in the spectral domain, but we still need to compute these matrices D and then project them. The point is that there are ways to either approximate these distance matrices from the solution of the heat equation, or actually directly approximate their band limited projection. Basically, this phi transpose dx phi. There are efficient ways to do it, again, using the heat equation, or we can use a different quantity like the diffusion distance, which is naturally computed in this domain. So basically, there is no need to work in the original space, in the original Euclidean basis, in the standard basis, where the number of nodes can be intractably high. We can work directly in the spectral domain when we can do a meaningful truncation of the number of basis functions to something that, of course, is controlled by the amount of blur or the features, the minimum feature size that we would like to be able to discern. Okay. And again, this L2 distance. Essentially, what we had is some kind of distance between two distributions, one crisp singleton distribution of the distances dx, And this one, this P transpose dyP, can be thought of as a probability distribution of distances on Y. And there are more meaningful distances between distributions, like the Kullback library divergence, rather than the trivial Euclidean distance. So all this, again, can be done. We didn't really do this properly, but even the toy experiments, the toy settings that we tried in these papers actually worked extremely well on shapes. And again, the big advantage of what I'm showing here is that practically everything that we did can be improved. Okay, so in the time that remains, how much time do I have?
10 to 15 minutes.
Okay, so I will try to wrap it up quickly. So one question I think that I promised you, and it is still unanswered, is how the heck we go from this functional correspondence back to the pointwise map. So you found this operator C or this operator T that you projected back onto the standard basis. How do we get a permutation, right? We want a bijection. So suppose I have the same number of points here on X and here on Y. How do I get a permutation matrix, right? Because this is what we maybe in some applications eventually are interested in. So the original functional map paper and many papers in this literature, they just look for nearest neighbors in that functional map domain. And if you look for nearest neighbors, you are not guaranteed to have a bijection. The map, for example, can be not surjective. So if you do texture transfer, so these green regions that you are seeing on the right, these are points that have no pre-image in X in the left-hand shape. So basically, the map is not surjective. And you can do some improvements, doing better algorithms, but again, the map is not guaranteed to be surjective. So we want a guaranteed bijection, and we want it to be constructed in a meaningful way. So because I didn't, unfortunately, Avi, you need to improve. I don't have a 4-dimensional screen here on Zoom, so I will need to do a 2-dimensional analogy. So let's take two 1-dimensional shapes. Of course, correspondence between 1-dimensional shapes is a boring and interesting problem, but this is just a visualization of what happens in higher dimensions. So I have this horse and these dog shapes, two 1-dimensional shapes, two contours. I can construct their product space. The product space for these two closed curves will be a torus, right? The product of two circles is a torus. And of course, I can equip them with some coordinate system. The correspondence between these two shapes would be a curve in this product space, right? Let's call it pi. It's a closed curve in the product space. So basically, a point xy on the curve means that point x is in correspondence with point y, okay? So think of this as a representation of a permutation matrix, a continuous representation of a permutation matrix, right? So instead of drawing the torus, which is a little bit nasty, I will draw its parameterization domain. Just remember that you need to glue these top and bottom ends and the left and the right ends. So this would be the parameterization of the torus. And then my correspondence is this nice diagonal matrix if I arrange the coordinates appropriately, or it can be any shifted diagonal. And suppose I have noise in this correspondence. So these 2 points are misplaced. They are noisy. So this point x, instead of mapping to yj to this point yj, it maps to yi here on the belly of the dog. And this point is also confused with the other point here. Okay, so this is what we get, a noisy correspondence. So what I'm going to do, I'm going to diffuse this image on X. So instead of having this crisp point, I would have some bell distribution, you see? Basically, I just blurred the rows of this matrix. Then I'm going to blur the rows of this matrix on Y, okay? And this is what I get, this blurred correspondence. And now what I'm going to do, I'm going to find the best bijection that maximizes this probability. So find me the most probable bijection, the most probable permutation, right? So so I start with this blurred probability distribution. Now find me a crisp path again that maximizes this probability. And not surprisingly, what I'm going to get is this. So this blur has filtered out the noise. So let me just show it on another example, 1D illustration. So I have these 2 points, the red and blue. This is my domain X. I first blur them on X. So a crisp singleton, a delta, becomes a bell. The other delta also becomes a bell. Now I map it to domain Y with the correspondence pi, and 2 points are misplaced. You see, these 2 points are misplaced. But now when I diffuse them on Y, again, the modes of these 2 distributions correspond to 8 and 20. Okay, so basically this noise is gone. Unless I have some systematic bias in the noise, this kind of noise is attenuated by this alternating diffusion on X and Y. So basically, this leads to an algorithm that we call product manifold filter, or PMF for short, and this is the result of the pre-processing that I was showing before. We start with some initial correspondence represented as pi n. I'm writing pi, but it doesn't need to be a permutation. It can be noisy, it can be sparse, so not all points are presented, are given with their correspondence, or it can be a distribution. It can be some kind of a blurred result probability density that comes, for example, from the functional map framework that we've seen before. Then I'm going to apply this diffusion kernel kx on the right, which amounts to diffusion on x. I will apply a diffusion kernel ky on the left, which amounts to diffusion on y. And then I will project it into the space of permutation. This projection amounts to solving a linear assignment problem. Okay? It is a solvable problem. It's not an easy problem to solve, but it is solvable. It can actually scale very well. The best algorithm, the lowest complexity algorithm that is known for this problem is the auction algorithm that was invented by Bert Sekas. And it can be also done in multiple scales if there is a meaningful scale space structure for these domains. So we can scale this to tens of thousands of vertices in our experiments. And then we iterate until convergence. So essentially, we get, let's say you start with this correspondence that has just 20 corresponding points. So of course it is widely not surjective. You can see actually where the corresponding points fall in the shape. Here the error is 0 or close to 0. And this shows just the geodesic errors. Of course, these other points become increasingly distant from their ground truth correspondence. So this is the first iteration. After 5 iterations, you see the error decreases quite significantly and the texture looks good. This is just a magnification. You see how well the texture improved. Texture are basically, it shows well the high frequency details that improved a lot after these filtering steps. And again, just comparing ICP and CPD are just 2 standard algorithms to recover point-wise maps. They are not guaranteed to be bijective. This one is bijective by construction. Again, our cumulative distribution of the correspondence errors, 3 different ways of recovering point-wise correspondences processed with the product manifold filter, you get almost perfect correspondence. Okay? Same here, combined with the FMNet, the descriptor learning framework that I showed you before also gets almost perfect correspondence. So it gets from here to here after the preprocessing. Let me give a few concurrent alternative explanations to what is going on here. So we can think of this kernel magic as a quadratic assignment problem. So basically, so what we had was this, right? This was our kernel. This was our one iteration of product manifold filter. So we did this blur of correspondence at iteration k, and then projected it onto the space of permutations, solving the linear assignment problem. And this gave us the correspondence at the next iteration. Now, the quadratic assignment problem trying to match 2 kernels, kx and ky, would look like this. So we would like to solve this quadratic objective. Now, pay attention here, pi k was fixed. So it was a linear assignment problem. Here, pi is a variable. So because we have this product of 2 pi's, it becomes quadratic and not linear. The objective becomes quadratic. So essentially what product manifold filter is doing is a sequence of linearizations of the quadratic assignment problem. So we linearize the problem at some point pi k and solve a linear assignment problem. So essentially this objective can be written as the minimization of the discrepancy of these two kernels. Okay.
Alex, actually, there is a question that maybe
Yes,
you
please.
want to clarify why
Yes,
the
I
diffusion
don't see
step is needed.
why the diffusion step is needed.
Yeah.
The diffusion reduces noise. If we have noise in the correspondence, the diffusion step removes noise, and then we project it back onto the space of crisp bijective correspondences. So basically, we have this sequence of sharpening and blurring steps that improves the correspondence quality. I will show you some, in my opinion, surprising extreme cases of this procedure. Okay, and just bear with me for a few minutes. So another way of looking at it is to see the quadratic assignment problem is Dirichlet energy minimization, or bending energy, elastic energy minimization in the product space. So Dirichlet energy minimization on X, on some space X, we would like to minimize this inner product of F transpose, this quadratic form with the Laplacian of X. Okay, subject to some constraints, of course, otherwise it has a trivial solution. Okay, so this is called the Dirichlet energy or bending energy, right? So instead of minimizing this Dirichlet energy, I can write maximization of, instead of the Laplacian, I will take the negative exponent of the Laplacian. This is called the heat kernel at time t. So minimizing this energy amounts to maximizing this quadratic form, okay? And basically this Laplacian is a diffusion kernel. T governs the amount of diffusion. The bigger is T, the wider is the spread of the kernel and the more diffusion happens, okay? So I'm maximizing this quadratic form with the diffusion kernel. Now, kernel matching energy, this matching energy, can be thought of, can be written as, so if I write pi as a vector, what is written here, kx and ky, it's a product of two kernels. This is this tensor product of two kernels. And this can be thought of as a kernel, a separable kernel on the product space. Or, and again, now you see the analogy, right? So this is maximization of this quadratic form with the product kernel. It can be thought of as a Dirichlet energy minimization on the product space X and Y. So if you again go back to our analogy of what correspondence is on the product space, so a product space for two-dimensional shapes would be a four-dimensional non-Euclidean manifold. The correspondence would be some kind of a two-dimensional membrane embedded in this manifold. And it will be very bumpy. And if it is bumpy, its Dirichlet energy is high. Think of this as elastic energy of a spring. And we would like to smooth this spring. We would like to remove all these bumps. And removing these bumps makes it smooth. It reduces the Dirichlet energy. So this is essentially what this product manifold filtering does. Again, another interpretation that I told you is this iterated blurring and sharpening. So basically, we apply this diffusion kernel. We can write it in the spectral domain. This is our correspondence C, right? And basically, this is what is written here is a low-pass filtering of the functional map C. So essentially, this exponential acts as a low-pass filter. The higher is the frequency, which is encoded by these eigenvalues lambda, the more is the attenuation of the filter. So we are essentially killing the high frequencies. This is what the diffusion kernel does. So essentially, we start with. So
the time is about to expire. So
I will show you some extreme examples, and I'm done. So extreme example input are these two corresponding points. So I know the correspondence between these two red points here and here on the tail and on the leg of the horse, matched to the corresponding 2 points on the elephant. These rainbow maps are the correspondences that we inferred using the product manifold filter. Like colors mark corresponding points. So you see, from 2 points, we were able to infer dense correspondence on the entire shape. This is an extreme example of two shapes that do not match. There is no continuous map between this contour and this two-dimensional surface, but still we find a meaningful correspondence. And this is an example of, again, a discontinuous match. We start with a random initialization on this torus. which we match to the sphere. There is no continuous map. So after 3 iterations, we get this. This is a nice smooth map, except this cut. Of course, it needs to be discontinuous. And this cut seems to minimize its length. It actually always converges to this kind of a cut. So we still don't understand why, but basically it allows to filter correspondences in really extreme conditions like the one that I'm showing here. So I will finish here. Thank you very much for your attention. I would obviously appreciate any questions. And as I mentioned before, Amit will show some additional interesting results from this line of works on shapes, also more related to graphs. And I'm just reminding that there is a plethora of works, not only from my group, of course. There are several groups that work on these techniques that can be adapted to graphs. I believe there is a wealth of tools that are largely unexplored in the graph analysis community that could be very, very useful, especially for large graphs. Okay, thank you very much.
Thank you, Alex. Very